This video, we solve problem 8 from section 8.4 of the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. This is in the Trigonometric Substitution section. Now remember, there are 3 trig antiderivatives, or inverse trig antiderivatives that we're familiar with. There is the antiderivative of 1 over the square root of x, or a squared minus x squared, which gives us an arc sine of x over a plus c. There's another one that looks like this. The integrand is 1 over a squared plus x squared. The antiderivative of that function is 1 over a times the arctangent of x over a plus c. And then finally, our third is the integral of 1 over x times the square root of a squared, or excuse me, x squared minus a squared with respect to x, which gives us an arcsecant of the absolute value of x, all divided by a plus c. And actually that has a 1 over a factor as well. Okay, so if we have an integrand that matches one of these exactly, we're going to get an inverse trig function. We'll either get the arcsine function, the arctangent function, or the arcsecant function. But if it doesn't match this exactly, we might be able to use u substitution. Let's say that there was an x in this numerator. If there was an x in this numerator, I could use u sub. I wouldn't get an arcsine from this. Or if there's an x in this numerator, I would get a u substitution here. And if there was an x squared in this numerator, one of those x's would reduce and I'd have an x over the square root of x squared minus a squared, and I could do a u sub there. So if the rule applies, apply it. If there is an x here or an x here or an x squared there, we'll simplify and we'll use a u sub. Now, if the rule doesn't apply and u sub is not appropriate, but it looks like one of these, then we make an appropriate trigonometric substitution. So the idea is if it looks like an arcsine because it has an a squared minus x squared in it, but it's not an arcsine and it's not a u sub, we make a sine substitution. Or if it looks like an arctangent, but it's not an arctangent and it's not a u sub, but it has that a squared minus x or a squared plus x squared in it. If it looks like an arctangent, but it's not an arctangent, you make a tangent substitution. And finally, if it looks like an arcsecant and it's not an arcsecant and it's not a u sub, then we'll make a secant substitution. So when I look at this integral, the first thing that I see is an x squared minus a squared. And that looks like this x squared minus a squared here. Now I can't use u substitution because the derivative of this would involve a 2x times dx. And we do have an x, but it's in the denominator. That x would have to be in the numerator in order for us to do a u sub from here. So it's not this exactly, but it kind of looks like that, and it's not a u sub, so we're going to make a secant substitution. So let's write that down. Since the integrand involves an x squared minus a squared, we're going to make a secant substitution. And the secant substitution that we make is x will equal a times secant of theta. Excuse me. All right, so now we're going to go through our 4-step process for evaluating an antiderivative using trigonometric substitution. The first step in that process is to prepare to substitute. So we are going to identify a, we'll define x, we'll compute dx, and because we've got that square root of x squared minus a squared, we're going to simplify that square root, and we're going to simplify that in terms of theta. Now, before I do that, I want you to just notice the difference between this substitution and the arcsine or the sine substitution. With arcsine, you've got a number minus x squared. With arcsecant, you've got x squared minus a number. When I see that x squared minus 25, it might be tempting to make a sine substitution here, but that would have to be in the reverse order. This is a number minus x squared, and I've got an x squared minus a number. Since this is x squared minus a number, I'm making the secant substitution and not the sign substitution. So we will identify a. A squared is 25. So a is the square root of that. That's 5. And x is a times secant of theta. Then we compute dx, because we need to write all of this in terms of theta. Dx is 5 times the derivative of secant of theta. Derivative of secant of theta is secant of theta times tangent of theta. Don't forget to multiply by d theta to get that differential of x. And then we want to simplify the square root of x squared minus 25, given this substitution. So we're replacing x with 5 secant of theta. So I replace this with 5 secant theta right here. Now remember from your algebra class that if you take, a product and you square it, you need to square each of those factors separately. So this 5 secant of theta is actually 5 squared, which is 25, times secant squared theta. And then the 25s can be factored out. Both of these terms have a 25 in common, so we can take that out. And that leaves us here. And then we remember from trig that 1 plus tangent squared of some angle is secant squared of the same angle. So if I solve for tangent squared, I get tangent squared is actually secant squared of that angle minus 1. So this secant squared of theta minus 1 is actually tangent squared theta. Now, when we take the square root of this, we always get a positive answer. The square root of 25 is 5, and the square root of tangent squared is tangent as long as tangent is positive. So it's actually the absolute value of tangent. If tangent is negative, we're going to take its absolute value because a positive square root will only give us positive answers. Now, if they don't give you any restrictions on x here, there's no corresponding restrictions on theta. Without some stated restriction, we'll just assume that we're on an interval where tangent of theta is positive. So we'll say that this is equal to this when tan theta is positive, and I wouldn't worry about it too much more. If you want to discuss why that's true, we can discuss it. There are also some videos on the playlist, the Calculus 2 playlist, that will show you why that's true. Okay, so we've prepared to substitute. Now we're going to substitute. We're going to write everything in that integral entirely in terms of theta. And of course, the point of that is to be able to anti-differentiate it. So we're substituting, simplifying, and anti-differentiating because we did not have an antiderivative rule for this, but hopefully after we substitute and simplify, we will have something that we can anti-differentiate, perhaps using basic rules or maybe one of our trig integrals guidelines from the previous section. So this is what we had. We had the square root of x squared minus 25 over x times dx. Now I am literally replacing things with other things. This square root of x squared minus 25, I simplified that already. I don't have to substitute in x equals 5 secant of theta right here because I've already simplified this. I already did the work. The square root of x squared minus 25 turns out to be 5 tangent of theta, provided we're on an interval where tangent is positive. So we're replacing this with 5 tan theta. X is replaced by 5 secant theta. And dx is replaced by 5 secant theta, tangent of theta, d theta. Okay. And of course, you're multiplying. You want to simplify wherever you can. The 5s reduce, the secants reduce, and you end up with an extra 5, which I can factor outside of my integral, and then a tangent of theta times a tangent of theta, which is a tangent squared theta. Then you say to yourself, do I have a rule for that? And we actually don't, but we do have a rule for secant of theta. The antiderivative of secant squared theta, is tangent of theta. And I can write this tangent squared of some angle as secant squared of the same angle minus 1. And I've got a rule for that and a rule for that. So that's the substitution that we will use here. Replace tangent squared with secant squared minus 1. And then compute the antiderivative. The antiderivative of secant squared is tangent. The antiderivative of 1 with respect to theta, this is not an x, it's a theta, is theta. Don't forget to add c if you want. You can distribute the 5. You don't have to. You could always do that later. Okay, so the trigonometric substitution was created so that we could take this that we didn't have an antiderivative rule for and write it in a new form so that we would have an antiderivative rule for that. And with a little bit of a trigonometric a little bit of an application of a trigonometric identity, we were able to get it into a form we had a rule for, and we were able to antidifferentiate. But this is never the answer. We are looking for a function of x because we want to be able to differentiate that function of x and get this integrand back. So in order to get that function of x, we need to write this answer in terms of x. In order to write this answer in terms of x, we're going to draw a triangle. We're going to draw and label the sides of a triangle. And it's a right triangle. Using our original substitution, which in our case was x equals 5 secant of theta. Now, I don't tend to think in terms of secant, cosecant, and cotangent. I still tend to think in terms of sine, cosine, and tangent. So I will probably restate everything in terms of sine, cosine, and tangent, and then use reciprocal identities to go the other way. So we've got x equals 5 secant of theta. And we want to label 2 of the sides of this triangle using this fact. The first thing that we do is we solve for secant of theta by dividing both sides by 5, and then I just switch the left-hand side and the right-hand side. And now I'm here. But again, I don't think in terms of secant. I do think in terms of cosine though. So I will take the reciprocal of that. 1 over secant is cosine. So I'm flipping that to get cosine. Flip this and you'll get this. And then remember cosine. Remember your trig class and mnemonics. So ka-toa. Cosine is adjacent over hypotenuse. So this, you could say secant is hypotenuse over adjacent, or you could just flip that and say that this is adjacent over hypotenuse. So when this is theta, the side adjacent to theta is 5 when the hypotenuse has length x. That's what that's saying for that particular angle, theta. Now using the Pythagorean theorem, we can find this other side, a squared plus 5 squared is equal to x squared. Subtract that 25 from both sides. Take the positive square root because we're talking about lengths. And a turns out to be the square root of x squared minus 25. Notice that that is the same square root that we saw in our original integral. That will always happen when you are using the Pythagorean theorem to find that third side of a triangle in the middle of a trig substitution problem. Okay, so now we've got our labeled triangle, and that labeled triangle will allow us to find tangent of theta in terms of x. So tangent of theta is opposite over adjacent. The side opposite theta is the square root of x squared minus 25. The side adjacent to theta, that's next to theta, that's not the hypotenuse, is just a 5. So that's what goes in here. We have 5 and we're multiplying by this tangent function. And then we're subtracting 5 times theta. Now this one is a little tricky for some students, but it's actually not too bad at all. You already know from your original substitution that secant of theta is equal to x over 5. In order to get rid of the secant, you will take the arcsecant of both sides. Because remember, the arcsecant and the secant are inverse functions. They undo each other. Let's just use the end of this paper right here. Got secant of theta on this side equals x over 5 on this side. And I'm taking the arc secant, oops, there's a c missing, of the secant of theta. And I'm setting that equal to the arc secant of x over 5. And the arc secant of the secant of theta is just theta because those two inverse functions undo each other. And so it turns out that theta is just arc secant of x over 5. So that's what we will substitute right here. And that's actually not something that you have to memorize. It is on your sheet of guidelines. Plus c. So we drew and labeled the right sides of our triangle. We used the triangle to come up with these expressions here. And then of course, the final step is to substitute and simplify. So we are writing that answer in terms of x rather than theta, using the sides of the triangle. These 5s reduce, and it turns out that we get the square root of x squared minus 25 minus 5 times the arc secant of x over 5 plus c. Now, I'm not going to do it this time. In the last video, we did this, but we could take the derivative of this and simplify. After taking the derivative of this and simplifying, I guarantee, well, provided I didn't make any mistakes, I would guarantee that the derivative of this is actually equal to that integrand. I'm not going to do that exercise now, but you're welcome to do it and check our work. So, okay, again, it looks like x squared minus a squared. We make the secant substitution. Prepare to substitute. Identify a, define x, compute dx, simplify the expression under the radical. Then you replace everything. The radical expression was replaced with this. The dx was replaced with this. The x was replaced with that. Simplify. If you need to, look up your trig integrals guidelines to get you from here to here, to get that integral in a form that we can antidifferentiate. Antidifferentiate it, and then draw a triangle so that you can write this answer in terms of x. Use your original substitution to label the sides of the triangle. There's going to be a third side. Use the Pythagorean Theorem, or just look at your guidelines. And then look at the answer that you have here. This has a tangent of theta in it and a theta. That means that once we draw that triangle, I need to use that triangle to find tangent of theta in terms of x, which I can using opposite over adjacent, and find theta in terms of x, which did not require the triangle. It required this original identity and taking the arc secant of both sides. Then you substitute. So you write this in terms of x and you write this in terms of x and simplify, and you're done. I hope that helps you. Let me know if you have any other questions.